Just getting set up. Quick sound check as well. Just getting set up. Quick sound check. Alright, we're live on YouTube. We're just gonna wait for X to hit, and then we will get the show on the road because I want to see if I can knock this out of the park tonight and complete. Right, we're live on all platforms, so let's get to it and smash this out. Okay, so we were on early today. We got through 4 lesson chapters of this. We got 1, 2, 3, 4, 5, 6, 7 left. Let's just see how far we can get through. If we can get to the end, great. If not, we have to come back next week. Then we have to come back next week, but let's try. So, as clause in SQL. So sometimes we need to structure the data we return for our queries in a specific way. An as clause allows us to alias a piece of data in our query. The alias only exists for the duration of the query. As keyword. The following queries return the same data, this and this. The difference is that the results from the alias query would have column names ID and name instead of employee ID and employee name. Throughout this course, you only use aliases when requested. Probably because you could cheat the system with using them. So that's probably why. So a user has asked us to find all the transactions on their account from their grandma. We thought it would be fun to rename the note field to birthday message because we noticed all the transactions from grandma are birthday messages. So return the amount and the note fields from the transactions table where sender ID is 10, grandma. The note field should be renamed to birthday message. Okay, let me read that again. So return the amount and the note field, so select amount, amount as note as birthday underscore message. Put it on things, so from transactions where sender underscore ID equals grandma. There we go. SQL functions. So SQL is a programming language, and like nearly all programming languages, it supports functions. We can use functions and aliases to calculate new columns in a query. This is similar to how you might use formulas in Excel. A calculated column is a new column that doesn't exist in the original table, but is created on the fly when you run a query. So IIF function. So in SQLite, the IIF function works like a ternary. For example, so IIF, car A is greater than car B, then car A is bigger, otherwise car B is bigger. If car A is greater than car B, this statement evaluates to the string car A is bigger, otherwise it evaluates to car B is bigger. Here's how we use the if and a directive alias to add a new calculated column to our result set. So select quantity if quantity is less than 10, order more, or otherwise in stock as directive from products. Assignment. We need to look at oh no, I didn't want to go to that. I wanted to close it. We need to look through a cache pile's transaction data and determine whether or not any of the transactions need to be audited. Return all the data from transactions table. So select all from transactions. Actions. Table and add an extra column at the end with the alias of audit. Okay, so then it's going to be IF, and it's going to be was underscore 6 was underscore successful equals true. Then no action required as audit. No action required, or perform an audit. And transactions. See how that does. Okay, I think that's it. So boom. Oh, whoops! I forgot to put on the magic juice. Here we go. So between, we can check if values between two numbers, if values are between two numbers using the where clause in an intuitive way. The where clause doesn't always have to be used to specify specific IDs or values. We can also use it to help narrow down a result set. Here's an example. So select employee name and salary from employees where salary between 30,000 and 60,000. Pennies, I'd imagine. This query returns all the product names where the quantity was not between 20. This query returns all employees' name and salary fields for any rows where salary is between 30 and 60,000 inclusively. We can also query results that are not between two specified values. So this query returns all the product names where the quantity was not between 20 and 100. We can use conditionals to make the results of our query as specific as we need them to be. So assignment, we need to see how many young adults are using CashPal. Query our users table to find the name and age fields of users between the age of 18 and 30. So select name, age from users where age between 18 and 30. Ta-da! Distinct. So sometimes we want to retrieve records from a table without getting back any duplicates. For example, we may want to know all the different companies our employees have worked at previously, but we don't want to see the same company multiple times in the report. So select distinct. SQL offers us the distinct keyword that removes duplicate records from the resulting query. So select from resulting query. Select distinct previous company from employees. This only returns one row for each unique previous company value. Assignment. CashPal executives want to know which countries we have customers in. We store country code data as a column on the users table. Run a distinct query to get all the unique country codes from the users table. So select distinct country code from users. Is that it? Boom. I just ran it without even testing it, but that's fine. Logical operators and. So we often need to use multiple conditions to retrieve the exact information we want. We can begin to structure more complex queries by using multiple conditions together to narrow down the search results of our query. The logical AND operator can be used to narrow down our result sets even more. So AND operator. This only retrieves records where both shipment status is pending and quantities between 0 and 10. Comparison operators. All the following operators are supported in SQL. The equals is the main one to watch out for. It's not double equals like in many other languages. SQLite does allow for double equals, but it's not a good habit to get into, as other dialects of SQL will not recognize double equals as a valid syntax. So there's equals, less than, greater than or equal to, less than or equal to, greater than or equal to, or not equal. Yeah, I've not seen it done like that. I don't really normally do that, but yeah. Assignment. The legal restrictions in Canada have changed. The way that we have to handle Canadian miners, cash pals transactions is more strict. We need to find all of those users so we can see how many users this change affects. Write a query that retrieves all of the columns from the users table who are from Canada and are under age 18. So select all from users where from Canada, so country code is equal to CA, and I guess age is equal to under the age of 18, so 18. Or, as you probably guessed, if the logical AND operator is supported, the OR operator is probably supported as well. This query retrieves records where either the shipment status condition or the quantity condition are met. Order of operations. So you can group logical operations with parentheses to specify the order of operations. This and that or the other. Assignment. The laws have changed again. Now we need to see how many affected users meet this criteria. So users who are from the United States or Canada and are under 18. Write a query that retrieves the count of every user, renamed as just junior count, that matches that matches the conditions above. So select count all as junior count, from users where and age is less than 18. So I guess country code is equal to US, or country _code is equal to CA. So it does. You can count 3. Boom. Well, I reached level 80. Arch Sage. In another variation to the where clause we can utilize is the in operator. In returns true or false if the first operand matches any of the values in the second operand. The in operator is a shorthand for multiple or conditions. These two queries are equivalent. Another variation where clause we can utilize is the in operator. In returns true or false if the first operand matches any of the values in the second operand. The in operator is a shorthand for multiple or conditions. Okay. Right, yeah, makes sense. Hopefully you're starting to see how querying specific data while using fine-tuned SQL clauses helps reveal important insights. The larger a table becomes, the harder it becomes to analyze without proper queries. So assignment, we want to know which of our users are from North America. Write a select statement that returns name and age. So name, age, from users, I guess, users, and country code, country _code, fields for every user in the US, CA, or MX. So we're country code, and it's going to be US, CA, or MX. I'm pretty confident. Just going to hit go. Push. Sometimes we don't have the luxury of knowing exactly what it is we need to query. Have you ever wanted to look up a song or a video, but you only remember part of the name? SQL provides us an option for when we're in situations like this. The like keyword allows for the use of the modulo and the underscore wildcard operators. Let's focus on modulo first. So the percent operator. The percent operator will match 0 or more characters. We can use this operator within our query string to find more than just exact matches depending on where we place it. So select all from products where product name like banana. So product starts with banana, product ends with banana, product contains banana. Assignment. Our HR team is dealing with a ticket from one of our users, but they're having trouble pulling up their record in the database. They are pretty sure the user's name starts with Al. Write a query that returns all the fields for records where the user's name starts with Al. So let's select all from users where name like starts with Al percentage. Run it. Boom, Bishko. The underscore operator. So as discussed, the percentage wildcard operator matches 0 or more characters. Meanwhile, the underscored wildcard operator matches only a single character. So the query above matches products like boot, root, foot. The query above matches products like shoot or groot. HR has been able to narrow down their query further. They want a report of all user data for users whose names start with Al and exactly 5 characters long. So we'll do it again. So select all from users where name is like and then 1, 2, 3. I'm pretty confident. Boom, we got it. So wildcards quiz. Example 1, example 2. So which describes the values that match example 1? So values that start with or. Nope, have 3 characters exactly. Values that start with or and are at least 3 characters in length. Values that start with or and are at least 3 characters in length. So, value ends with or. It starts with or and at least 3. That one. Which would not match example 2? So 1, 2. Which would not match? Singing. Okay, discount programs. So CashPal has launched 2 discount programs. All users over the age of 55 will qualify for a senior discount. All users from Canada, country code CA, qualify for a Canada Day discount. Users who qualify for either discount will get 10% off. Assignment. Write a query that returns every user from the users table, including all columns, along with additional column called discount percent. Right, let's start with that. So select all and an additional column called discount percent. So if it's going to be from users along with additional column. So country, so exchange discount. So it's going to be age is greater than 55, or country code is equal to CA. Then the discount percentage column should have an integer of 10 or 0 depending on whether the user matches. So like there and there as discount underscore percents. Okay, I think that's it. Woohoo! Structuring. Okay, so structuring. So limit. What's the course after this one, by the way? I was just like thinking in my head then, what's the one after this one? So SQL, build a blog aggregator in Go. Okay. So sometimes we don't want to retrieve every record from a table. For example, it's common for a production database table to have millions of rows, and selecting all of them might crash your system. The limit keyword has entered the chat. The limit keyword can be used at the end of a select statement to reduce the number of records it returns. So the query above retrieves all records from products table where the name contains the word berry. If we ran this query on the Amazon database, it would almost certainly return a lot of records. The limit statement only allows the database to return up to 50 records matching the query. This means that if there aren't many records matching the query, the limit statement will not have an effect. A lot of users have been using CashPal to pay other users for lunch. Let's take a look at a sample of that. Write a query that returns all rows and fields from the transactions table. So all from transactions. Any record where note field has the word lunch in it. So note like lunch, and then the query should be limited to the most 5 records. I think that's spot on. So there we go. Got it. Limit quiz. Limit 5 will always return exactly 5 records. False. Why might you use a limit clause? To get as much data as possible, to avoid selecting a huge amount of data and causing strain on the system. I wouldn't. System performance is an ops person's problem, because I'm a machine learning engineer and don't care about efficiency. Fair enough. Order by. So SQL also offers us the ability to sort results of a query using order by. By default, the order by keyword sorts records by the given field in ascending order, or AS for short. However, order by does support a descending as well with the keyword desk. Examples. This query returns the name, price, quantity fields from products table sorted by price in ascending order. Order by price, yeah. This query returns name, price, quantity of the products ordered by the quantity in descending order, so ascending is default. Assignment. Write a query that lists all the records in the transactions tables where, so select all from transactions where amount between 10 and 80. The results are sorted by the amount in descending order. Then okay, so then order by amount descending. I'm pretty sure it's spawn, so just hit go. Order by quiz. So example 1 is sorted by age in descending. Which query would potentially return the data in example 1? Select all from people, order by age. Order by age descending. Select all from people, order by age ascending. Select all by age. One of them is trying to trick you out there with like a syntactical trick, just being in the wrong order. So when using both order by and limit, the order by clause must come first. Assignment. A HR employee going to the Git history, Git repository where we store all the queries and try to update one himself. Fix the bug in the SQL query, so I'll just do that. Order by, boom. Happy days. Security breach. Bad news. CashPal suffered its first security breach. One of the interns leaked a sensitive file that contained some user passwords. Even worse, the user table has passwords stored as plain text. Luckily, we know which passwords were leaked, so we can warn these specific users before we move to a modern password storage system. Assignment. Create query returns the name and username for every user with a password equal to, okay. Select name, username from users where password in and order order the records so that the names are in alphabetical order. So order by name, name ascending. So it's going to be one of these. It's going to be back end dev. We love Boot.dev, of course we do. SQL rocks. See how it does? Bingo. Aggregations. Getting through is pretty nippy. So what are aggregations? An aggregation is a single value that's derived. So how many things have got in this? Okay, 11. An aggregation is a single value that's derived by combining several other values. We performed an aggregation earlier when we used the count statement to count the number of records in a table. Why aggregations? Data stored in a database should generally be stored raw. When we need to calculate some additional data from the raw data, we can just use an aggregation. Take the following count aggregation as an example. So all that. So this query returns the number of products that have a quantity of 0. We could store that count of the products in a separate database table and decrement it whenever we make changes to the products table, but that would be redundant. It's much simpler to store products in a single place. We call this single source of truth, and run an aggregation when we need to derive additional information from the raw data. So assignment. The front-end team is building a dashboard page in CashPal. We need to be able to provide them the number of successful transactions for a given user. So return the number of transactions. So let's pass the thing. Whoops. No. Select all. Count from transactions where user ID is 6 and was successful is true. Remember to use a wildcard unless you. So where user ID is equal to 6 and was underscore successful is equal to true. Is that right? Bingo. Sum. The sum aggregation function returns the sum of a set of values. For example, the query below returns a single record containing a single field. The returned value is equal to the total salary being collected by all of the employees in the employees table. So assignment, we need to be able to calculate the current balance for a given user because we don't yet store the running balance on each individual transaction record. Write a query returns the sum aggregation of the amounts for all of Bob's successful transactions. From transactions where user underscore ID is equal to 9. Confident on this one, so let's just go. Oh no. We need to calculate the balance. Write a query returns the sum of the amount for all of Bob's successful transactions. All right, I see. Whoops, I forgot that. And successful underscore. Is it like was successful or was underscore successful equals true? There we go. Forgot the what's bit. So max, as you may expect, the max function retrieves the largest value from a set of values. For example, max price from products. So this query looks through all the prices in the products table and returns the price with the largest price value. Remember, it only returns the price, not the rest of the record. You always need to specify each field you want a query to return. So assignment. Using max aggregation to return the age of our oldest cash pal user who is also an admin, alias the return age column, so to just be named age. So max where is underscore admin is equal to true. Whoops, users. There we go. Min. The min function works the same way as max function but finds the lowest value instead of the highest value. So select products, product name, min price from products. This query returns the product name and the price fields of the record with the lowest price. Assignment, use a min aggregation to find only the age of our youngest cash pal users in the United States in the users table. The country code of the United States in US, it is US. Alias, the returned age should just be column age. So age as age. So where country underscore code is equal to US. Okay. Group by. There are times we need to group data based on specific values. So SQL offers the group by clause, which can group rows that have similar values into into summary rows. It returns one row for each group. The interesting part is that each group can have an aggregate function applied to it that operates only on the grouped data. So example of group by. Imagine that we have a database with songs and albums. If we want to see how many songs are in each album, we can use a query like this. So select the album ID, count song ID as song count from songs. This query retrieves a count of all the songs on each album. One record is returned per album, and they each have their own count. So assignment, let's get the balance of every user in the transactions table, all in a single query. Use the combination of sum, aggregation, and the group by clause to return a single row for each user with transactions. So select the row each user must contain. It should be user _ ID and their balance. Balance sum of the amounts. So sum. Sum of the amounts. So let's get the balance. We're using transactions table. User query uses sum, aggregation, group by clause. So the row for each user should contain the user ID and some of the balance successful of their successful transactions. Okay, where was _ successful is equal to true. There we go. You need to read it in full, guys. You need to read it in full. Just like we may want to find the minimum or maximum values within a data set, sometimes we need to know the average. SQL offers us the avg function, similar to max, and avg calculates the average of all non-null values. So this query returns the average song length in the songs table. So assignment. Our marketing team is trying to determine the best marketing channels to advertise through, but they need more information about our current users. They wish to know the average age of users in the United States. So return a single value representing the average age of all users, where the country code is the US. So select average age from users where country code is equal to US. Bingo. So having when we need to filter the results of a group by query even further, we can use having clause. The having clause specifies a search condition for a group. The having clause is similar to the where clause, but it operates on groups after they've been grouped rather than the rows before they've been grouped. The query returns the album ID and count of its songs, but only for albums with more than 5 songs. So assignment, a new page in CashPal app. New page in CashPal app allows users to see how much money they've spent on a specific kind of transaction and alerts them if that amount is fairly large. Let's write a query that returns the total amount spent by each user on lunch when the balance is greater than 20. So return sender ID, the person spending the money, and a balance. Okay. So sender underscore ID and balance. Balance is the sum of all the amounts. Okay, so then sum amount as balance. Don't return any rows that have a null sender ID. Transactions. Okay. Every time you rows have a null sender ID. I think group by fills that out, doesn't it? He said. Only return transactions that were successful. Where was underscore successful is equal to true. The note must contain the word lunch to be part of the aggregation, and note like group by sender ID. Oh, 1 minute. Group by sender ID, aggregate balance must be greater than 20. Alright, come back to this 1 second. Right, back to it. So, group by the aggregated balance must be greater than 20. Order results by the balance in ascending order. Specifies a search condition for a group. Aggregate balance must be greater than 20. Am I going to teach you from basic? No, I'm not teaching here, guys. This is more like a follow along or just kind of watch me as I kind of go through things. If you want, sign up to Boot.dev yourself. You got to put the learning into your own hands. So the aggregated balance must be greater than 20. Order results by order by balance ascending. So I think I've got that. The note must contain the word relationship it's part of the aggregation. I think I've got that. Don't retain any null values. I think I've got all that basically. Let's see. Boom. That was a long query. Having versus where in SQL. So it's fairly common for developers to get confused about the difference between having and the where clauses. They're pretty similar after all. The difference is fairly simple in actuality. So a where condition is applied to all the data in a query before it's grouped by a group by clause. A having condition is only applied to the grouped rows that are returned after a group by is applied. This means that if you want to filter based on the result of an aggregation, you need to use having. If you want to filter on a value that is present in the raw data, you should use a simple where clause. In the example, should you use a where or a having clause to filter down to a specific class ID? Having. Oh no, sorry, it's in the original thing. Didn't see it there. In the example, should you use a where or a having clause to filter down classes of a particular size? Well, don't know what happened there. Alright, for now we're just going to have to stick with YouTube because for some reason the computer just decided to restart on its own, which is great.
When I started Walton Goggins Goggle Glass, I knew I'd be its fancy name and pretty face.
Right, okay, let's get back to it. I think this is all we're going to get for now. Like, Twitch is not responding for some reason, so... whatever, I guess. Don't really matter. X isn't going to pop up anything now because the scheduled stream was over, so... Right, let's get back to where we were. So we had the answer to this one. It was just the having. Okay, so round. Sometimes we need to round some numbers, particularly when working with results of an aggregation. We can use the round function to get the job done. The SQL round function allows you to specify both the value you wish to round and the precision to which you wish to round it. So round value precision. If no precision is given, SQL will round the value to the nearest whole value. This query returns the average song length from songs table rounded to a single decimal point. Assignment: fix the query so that it returns a whole number. Rename the result column to round age. So as round age average returns a whole number. Oh, whoops. So we put the whole thing in round. Here we go. Average ages. So the Cash Pal marketing team was able to optimize the advertising with the help of the user data we pulled. However, they now want you to query the average age of users for each country that the business operates in, not just the United States. So write an SQL statement that returns two columns: the country code, so country code, and the average age of users for records with that country code. So count. Oops, count. No, not count, sorry. Round. Average of age as average underscore age from users. Oops, users where Aki team is asked that we round the average age to the nearest whole number, and we rename the column that contains the average age to average age. So then it's going to be group by country underscore code. Bingo. So on chapter 8, subqueries, normalization, joins, and performance. So I think we're going to make it. I'm just going to pop another one on now so I don't have to top it up. Here we go. So subqueries. Sometimes a single query is not enough to retrieve the specific records we need. It is possible to run a query on the result set of a query within a query. This is called subquery. Subqueries can be very useful in a number of situations when trying to retrieve specific data that wouldn't be accessible by simply querying a single table. So retrieving data from multiple tables. Here is an example of a subquery. So select that where artist ID in, and then select that. In this hypothetical database, the query both selects all of the IDs, song names, and artist IDs from songs table. That are written by artists whose name starts with Rick. Notice that the subquery allows us to use information from a different table. In this case, the artist table. Subquery syntax, though. The only unique syntax to a subquery is the parentheses around the nested query. The in operator could be different. For example, we could use equals operator if we expect a single value to be returned. Assignment. So one of CashPal's customer service representatives needs to pull all transactions for a specific user. Trouble is, they only know the user's name, not their user ID. Use a subquery to return all transaction details for the user with the name David. So we're just going to select all from. So transactions where transactions so it's going to be users where what is it? User ID in select no, it's that way around. So transactions user ID in select user. I guess it's going to be user underscore ID name. I guess it's just going to be name, isn't it? So name from users where I guess like ID with the name with the name David. Is it none? So David is number 1. Whoops. Whoops, ID. There we go. So subqueries. Sometimes a single query doesn't have to retrieve specific records we need. Oh, right. Okay, we've already done that. A subquery is a technique for speeding up your database, creates a temporary table, allows you to query the result, set of a nested query. The example will return blank rows. Subqueries. Potentially many. Oops. Invoice subquery. So certain customers have been using their personal CashPal accounts for business expenses. CashPal is trying to contact these customers so they can upsell business accounts. Using a subquery, write an SQL statement that retrieves full user records for every user who matches the sender ID in a transaction with invoice or tax mentioned where anywhere in the transaction note and who is not an admin. So select all from users where sender ID, so where ID is in select and is underscore admin is equals to false. So select sender underscore ID from transactions where notes like in, and it's going to be invoice or tax. And who is not an admin? User matches the sender ID in a transaction with invoice or tax mentioned anywhere in the transaction note and who is not an admin. It is admin. It retrieves full user records for every user who matches the sender ID in a transaction with invoice or tax mentioned anywhere in the transaction note and who is not an admin. No. This isn't it for some reason. I'm not too sure. Want to make sure I get through this tonight, so I'm going to ask for help. What's wrong with this? Yeah, it's fine. Something trivial. Oh, I put it like that. Oh, that's why I have to put note again. Like, okay. There we go. I could have used it in, but it didn't let me before. So, no tables. So when working on backend application, this doesn't come up often, but it's important to remember that SQL is a full programming language. We usually use it to interact with data stored in tables, but it's quite flexible and powerful. For example, you can select information that's simply calculated with no tables necessary. So, assignment. Finance has found that people who have lived longer than 40 years need to start thinking about retirement. Write a query that returns all columns of all the users who are more than 40 years old. Unfortunately, this table awkwardly stores age in days in the age in days field. Use the subquery to convert 40 years to days and filter on that. Assume every year has 365 days. So, write a query returns all columns for it. Select all from users who are more than 40 years old, where age is greater than and we do 365 times by 40. age in days. Age in, let's call it days. Okay. SQL can only operate on data stored in tables. Incorrect. So normalization, last 3 chapters, normalization, joins, and performance. Okay, let's see how we do. Relational databases are powerful because of the relationships between tables. These relationships help us keep our databases clean and efficient. A relationship between tables assumes that one of these tables has a foreign key that references primary key of the other table.
The one thing you don't want to screw up when you're architecting your database is the relationships. One-to-one, one-to-many, many-to-many. These relationships need to be accurate. If you get that right, almost any other mistake is easily fixable. So let's do one-to-one. Say we have a table that contains all the students that attend Boot.dev. Every student row has a unique ID and an enrolled ID, so 2 columns. Now, say we want to also store the student's name. We could make a new table called student names with a name column, and then add a foreign key column like student ID to link the records together between the tables. But honestly, that wouldn't make a lot of sense. 99% of the time, when you have a one-to-one relationship, like the relationship between a student entity and their name, you should just add a new column to the existing table. So now the student table has 3 columns: ID, created at, and name. A student can only ever have one name, so we store it directly on the table. Now, what about a one-to-many relationship? Well, a student needs payment methods, right? And sometimes one fails, so we want them to be able to add multiple on file. We could add new columns, like credit card 1, credit card 2, credit card 3, and that would sort of work. But what happens when we want to add a 4th payment method? We would need to add another new column. And what happens when a specific student only has 2 payment methods? Well, we end up with some null columns. And what if we need to add nicknames to the payment methods themselves? Do we duplicate all the columns, like credit card 1 name, credit card 2 name? This approach gets really messy and honestly buggy pretty quickly. The correct approach is to recognize that a single student can have many credit cards, so we need a one-to-many relationship. We typically model that by using 2 tables: students and credit cards. The student table might have ID created at and name, and the credit card table might have ID created at card name and name. Then we can link or relate a student to their cards by adding a foreign key to the many side of the relationship. In this case, we add a student ID column to the credit cards table, and that ID should match the ID on the student table. So we can now have many credit card rows in the credit cards table that all point to the same single student ID. Now, say we want to add a student's classes to the database. Now, you might think this is another one-to-many situation, but if we follow the same pattern as before, we actually end up with a copy of every class record for every student that's in that class. For example, let's say we've got 2 classes, Computer Science 101 and Business 105. If 30 students are enrolled in each, and we've modeled it as a one-to-many relationship, then we'd have 30 student records and 60 class records. Most importantly, if we change the name of Computer Science 101 to CS 101, we need to update 30 different records to reflect the change accurately. And if we don't, we could have 15 students still in a class called Computer Science 101 and 15 students in a class called CS 101, even though it's the same class. So this approach is really prone to bugs. The right way to model it is as a many-to-many relationship, which we do by adding a 3rd joining table. Many students can be in the same class, and a single student can take many classes. So our schema will look like this: a students table with columns ID created at and name, and a classes table with columns ID created at and name. But we'll have 30 records in the users table and only 2 records now in the classes table. And the key difference is that now we have a students classes table with a student ID and a class ID. So to represent a student being in a class, we just add a record to the students classes table, and it represents the relationship between the 2. Now we can add any student to any class, and we have a single source of truth for each student record and for each class record. If we want to update the name of a class, we only have to update it in one place. So the joining table just manages the relationships, which in this case represents enrollment.
Good. So we've got one-to-one, one-to-many, and many-to-many. One-to-one. So a one-to-one relationship often manifests as a field or a set of fields on a row in a table. For example, a user will have exactly one password. Science fields might be another example of one-to-one relationship. A user will have exactly one email preference and exactly one birthday. Which is an example of a one-to-one relationship? A user's transactions, a university's professors, transactions note, a father's children. Transactions note. It's the same again. How would you model the relationship between a course and its name? One-to-one. So one-to-many. When talking about the relationship between tables, a one-to-many relationship is probably the most commonly used relationship. A one-to-many relationship occurs when a single record in one table is related to potentially many records in another table. The one-to-many relationship only goes one way. A record in the second table cannot be related to multiple records in the first table. So examples of one-to-many relationships: a customers table, an orders table, and an orders table. Each customer has 0, 1, or many orders that they've placed. A users table and a transactions table. Each user has 0 to 1 or many transactions they've taken part in. Assignment. It turns out that when we originally designed the cache pile database schema, we assumed that users would only have a single country they lived in. With digital nomads becoming a thing, it turns out many users have dual citizenship. Instead of a single users table where each user has a single country code, do the following. Remove the country code field from the users table. Create a new table called countries. So do create table countries. It's going to have an ID, an integer primary key. So integer primary key, country code, text, name as text, user score ID, as text. Integer foreign key to user tables ID field. I've forgotten how to do. Oh yeah, constraint. Okay. So it's constraint foreign key underscore users foreign key. So the foreign key is user underscore ID and references users ID. Integer. Missing that bit. There we go. Okay, many to many. So many to many relationships occur where multiple records in one table can be can be related to multiple records in another table. So examples of many-to-many relationships. So a products table and a suppliers table. Products may have 0 to many suppliers, and suppliers can supply 0 to many products. A classes table and a students table. Students can take potentially many classes, and classes can have many students enrolled. So a joining table. So joining tables help define many-to-many relationships between data in a database. As an example, when defining the relationship above between products and suppliers, we would define a joining table called product suppliers that contains the primary keys from tables to be joined. Then, when we want to see if a supplier supplies a specific product, we can look in the joining table to see if the IDs share a row. So unique constraint across 2 fields. So when enforcing specific schema constraints, we may need to enforce the unique constraint across 2 different fields. This lets multiple rows share the same product ID or supply ID, but it prevents any 2 rows from having both the same product ID and supplier ID. So assignment, we have another issue with our current user country relationship. In the current schema, a user can have many countries associated with it, but they're duplicate records. If 2 users are associated with the United States, we're creating 2 country records. It would be better if each country only had a single record. That way, when a country changes its metadata, for example, it decides to rename itself, we only have to update 1 record. Using a joining table to duplicate country data, remove the user ID field from the countries table. So create a new table called, create table users _ countries. I should have 2 fields, country _ ID, integer, add a unique together constraint on those ID fields. So integer, and then user _ ID, integer, unique. It's going to be country _ ID. Excuse me. User _ ID. Is that right? Ta-da! So database normalization. So database normalization is a method for structuring a database schema in a way that helps improve data integrity and reduce data redundancy. 8-minute video.
The academic definition of database normalization, but you can mostly just ignore it. Normalization is super important to understand. It seriously impacts the code that you write in the real world, but the technical category definitions are mostly just an academic exercise. That said, let's go over them in excruciating detail, and I'll give you the actual practical rule of thumb about how to use them at the very end. But first, what is normalization? Well, it's really just the practice of improving the structure or schema of a database so that it has less data redundancy, duplicate data, and more data integrity, which really just means correct data. So to put it simply, we want to store data in its simplest form with no copies, because copies can lead to bugs. For example, we might update one copy and forget to update the other copy, which gives us sort of this invalid state. Which one represents the truth? And normalization is a gradient. You can have a database that's more normalized or one that's less normalized. The more normalized the database is, the less duplicate data you have, and the more correct the data is likely to be. Now, academics have defined 4 different normal forms. First, second, third, and voice cod. As we move up from first to second to third to BCNF, the database becomes more and more normalized. Now, each form is just a set of rules. If the data in the database follows the rules, then the database is in that normal form. The rules build on each other. So second normal form has all the rules from first normal form plus some extra. Third normal form has the rules from second normal form plus some extra. You get the idea. So anyways, let's start with first normal form. It just has two rules. First, every row is a unique primary key. And two, there can be no nested tables. Now, rule number 2 is actually pretty easy to follow in practice. Most database systems don't even let you nest tables within each other, with the exception of like maybe embedding some JSON. But to understand rule number 1, let's say we have a users table with 2 columns, first name and age. And say we have a user in that table, Lane, who's 30. If another user signs up with the same name and age, Lane, 30, we get a duplicate row. And this is what first normal form is supposed to prevent, because no duplicate rows are allowed. To fix it, we can just add a unique ID column as the primary key. We'll give the first row 1 and the second row ID 2. Now, these ID numbers would be generated by the application so that they can't be duplicated no matter what the user's name or age is. Okay, so that's first normal form. Now on to second normal form. We still have to follow all the rules of first normal form, but there is one additional rule. All columns that are not part of the primary key must be dependent on the entire primary key, not just part of it. And a primary key is usually a single ID column, but you can have a table with a primary key that's a unique combination of 2 or 3 or more columns. For example, you might have a users classes table that maps users to the classes they're in, as a user ID column and a class ID column. User 1 is in class 3, 2 is in class 4, user 1 is in class 5. Now, there's not much point here in adding a third ID column because the unique combination of user ID and class ID does the job just fine. You can't enroll in the same class twice. That doesn't really make sense. When we use the term primary key in a software engineering sense, we're usually referring to an ID column or maybe a specific combination of columns that we've created a primary key around. But in an academic computer science normalization sense, primary key just means the smallest number of columns that can be used to uniquely identify a row in an actual data. So say we have a table with 3 columns: first name, last name, first initial. And then we have Lane Small, first initial L, Lane Brewer, first initial L, and Alan Small, first initial A. Now this table technically follows first normal form because there are no duplicate rows and no nested tables. But it doesn't follow the same. This also be a primary key by themselves because none have completely unique values. But we can choose a pair that creates first name and last name. Now with that definition of a primary key in mind, let's read the rule again. All columns that are not part of the primary key, in this case first initial, must be dependent on the entire primary key, not just part of it. The problem is that first initial is entirely dependent on just the first name column, which is a part of the primary key, not the whole primary key, so we broke it. So to solve this, we can create a new table. The first initial column there. It's a mapping table of first name to first initial. So we've got Lane, L, Alan, A. And in our first table, we just drop that first initial column. Now, both tables follow the rules of second normal form. And if we need to look up the first initial by the user's name, we just use that second table to do so. Now we don't have a duplicate mapping of Lane to L. We only store that relationship once. Now this might seem like a really silly example. Why would you store an initial alongside a name? You just calculate it when you need it. And it is kind of a simple example. But there are times in the real world where you will have a column that kind of depends on another column. And rather than storing it many, many times, you can extract it out into another table. Now on to third normal form. It follows all the rules of first and second normal form, but now adds one additional rule. All the columns not in the primary key must be dependent only on the primary key. So go back to the same example, but add a unique primary key column. ID. So we've got 1 Lane Small L, 2 Lane Brewer L, 3 Alan Small A. Now you might think that this is the same problem as before, and it kind of is. But technically, this table does follow second normal form because first initial is dependent on first name. And first name is not part of the primary key anymore because that's the new ID column. But fundamentally, we're still duplicating data. We know Lane maps to L, and we don't need to store that relationship twice. This table breaks third normal form because a column not in the primary key, first initial, is dependent on another column not in the primary key, first name. And again, we can solve this by moving the first name to first initial mapping to a separate table. Okay, last normal form. Voice cod normal form. It adds one final rule. A column that is part of the primary key may not be dependent on a column that is not part of the primary key. It's important to note that voice cod normal form, or VCNF, was invented after first, second, and third normal forms. Once they realized that there was still a way for duplicate data to slip into tables, even if a table followed third normal form. For voice cod normal form to matter, the database has to be in a very specific state. Say we have a table with 4 columns: release year, release date, sales, and name. And we fill it up with all of this data. In this table, we have several possible candidate primary keys. Name could be the primary key on its own, or it could be a combination of release year and sales. The date column could also be a primary key on its own. If we choose the combination of release year and sales as our primary key, the problem is that release year is fully dependent on the release date column. So we have a column in the primary key that is dependent on a column that's not part of the primary key. That doesn't break second or third normal form, but it does create duplicate data, and voice cod normal form fixes this edge case. Again, it says a column that's part of the primary key cannot be entirely dependent on a column that's not part of the primary key. Now, one way to fix this is to store year, month, and day in separate columns. But honestly, we could just get rid of the release year column entirely because we already have the more specific date column. Okay, so these were the technical definitions, the academic definitions of first, second, third, and voice cod normal forms. But here's what I want you to remember as a real-world software engineer, not a computer science academic. Unless you have a really, really good reason, usually performance-related, don't denormalize your data. Try to keep it as normalized as possible. And for the most part, we just want full normalization. Voice cod normal form, which when you ignore all of the other categories, we can talk about it much more simply. Just don't store redundant data. There should only be one way to represent the state that you're trying to represent in your database schema. Add unique primary key ID columns, and if you do that, you'll be just fine.
Yeah, very technical definitions there, and I don't think I'm not going to remember all of them off by heart and stuff. So to improve data integrity, data should generally be stored in raw form, not pre-computed. Pick the best example of data redundancy. 2 tables both contain fields that store a Boolean value. Each table has an ID field as its primary key. A user's address is stored in 2 different tables, a country table and a user's table, each containing a field called name. User's address. That one. So normal forms. So the creator of database normalization, Edgar F. Codd, described all different normal forms a database can adhere to. We'll talk in the most common ones. Yeah, okay. So which form has the most duplicate data? First normal form. Which form encourages the most accurate and up-to-date information? Voice cod, I guess, most strict. In the context of normalization, a primary key is made up of one of table columns. One to many, I guess. Okay, first normal form, second normal form, third, and voice. Okay. So to be compliant with first normal form, a database simply needs to follow 2 rules. It must have a unique primary key. A cell can't have a nested table as a value depending on the database you're using. This may not even be possible. Example of not first normal form. So name, age, email, they are all 2 duplicates. This table does not adhere to first normal form. It has 2 identical rows, so there isn't a unique primary key for each row. Example of first normal form. Simplest way, but not the only way, to get first normal form is to add a unique ID column. It's worth noting that you create a primary key by ensuring that 2 columns are always unique together. That works too. You should almost never design a table that doesn't adhere to a first normal form. First normal form is simply a good idea. I've never built a database schema where each table isn't at least in first normal form. So assignment, we hired an intern at CashPal, and the first task was to design design a new company's table. This table will store our business client's data. Unfortunately, the intern has committed the unforgivable sin. There's no primary key on this table. We could have entire duplicate rows. Add an ID as a field for the first column. It should be an integer and have a primary key. So ID, integer, primary key. Constraint on it. When you're done, the company's table will be in the first normal form. Skrabushka. Second normal form. So table in second normal form follows all the rules of first normal form and one additional rule, which only applies to composite primary keys. All columns that are not part of the primary key are dependent on the entire primary key and not just one of the columns in the primary key. Example of first normal form but not second normal form. In this table, hold on, let me read it again. All columns that are not part of the primary key. All columns that are not part of the primary key are dependent on the entire primary key and not just one of the columns in the primary key. Example of first normal form but not second normal form. In this table, the primary key is a combination of first and last name. This table does not adhere to second normal form. The first initial column is entirely dependent on first name column, rendering it redundant. Okay, example of second normal form. So one way to convert a table is to move to second normal form is to add a new table that maps first name directly to initial. This removes any duplicates. Second normal form is usually a good idea. You should probably default to keeping your tables in second normal form. That said, there are good reasons to deviate it, particularly for performance reasons. The reason being that when you have to query a second table to get additional data, it can take a bit longer. My rule of thumb is optimize for data integrity and data duplication first. If you have speed issues, denormalize accordingly. So assignment. Another developer on our team has created a joining table for the company's users many-to-many relationship. Unfortunately, they did it a bit weird. They included meta information about companies on the joining table. A good joining table simply has the IDs of entities in the relationship. It manages the relationship and nothing else. Any information about entities themselves belongs on their respective tables. Move the column that's out of place to its proper table. There we go. Whoops. Be sure to add it as the last column to the Alright, okay. There you go. Third normal form. A table in third normal form follows all the rules of second normal form and one additional rule. All columns that aren't part of the primary key are dependent solely on the primary key. Notice that this is only slightly different from second normal form. In second normal form, we can't have a column completely dependent on only parts of the primary key. And in third normal form, we can't have a column that is entirely dependent on anything that isn't the primary key. So example of second normal form but not third normal form. In this table, the primary key is simply the ID column. This table is in second normal form because first initial is not dependent on a part of the primary key. However, because it is dependent on the name column, it doesn't adhere to the third normal form. Example of third normal form. Yeah, okay. Third normal form is usually a good idea, so the same exact rule of thumb applies to the second and third normal forms. Optimize for data integrity and data duplication first by adhering to the third normal form. If you have speed issues, denormalize accordingly. So assignment. This rollout of business accounts is really causing some headaches for our development team. The company's table has been a disaster. Our database architect pointed out that the idea behind the size field is redundant. If a company has more than 100 employees, we consider it large, otherwise we consider it small. That's something we can calculate from the number of employees field rather than storing it separately. Remove the size column from the company's table by modifying the create table statement. Remove the size column. Oh yeah. Change the select statement to calculate a size field in the result set that works the same way. Okay. Size. Oops. So I guess. So what was it? Calculate a size field in result that's. Whoops. Is greater than 100, then it's was it large or small? Remember if as clause, yeah, I did that as size. Whoops. A size field in the result set that works the same way. Whoops, not some, just need to do that. There we go, silly me. Boyce Cod normal form. Boyce Cod normal form, a table in Boyce Cod normal form created by Raymond F. Boyce and Edgar C. Cod, follows all the rules of the third normal form plus one additional rule. A column that's part of a primary key cannot be entirely dependent on a column that is not part of the primary key. So this only comes into play when there are multiple possible primary key combinations that overlap. Another name for this is overlapping candidate keys. Only in rare cases does a table in third normal form not meet the requirements of Boyce Cod normal form. So example of third normal form but not Boyce Cod normal form. An interesting thing here is that there are three possible primary keys. Release year plus sales, release date, name. This means that by definition, this table is in second and third normal form because those forms only restrict how dependent a column that is not part of a primary key can be. This table is not Boyce Cod's normal form because release year is entirely dependent on release date. Example of Boyce Cod normal form. So the easiest way to fix the table in our example is to simply remove the duplicate data from release date. Let's make that column release day a month. Boyce Cod normal form is usually a good idea, so the same exact rule of thumb applies to the second, third and voice code normal forms. That said, it's unlikely you'll see voice code normal forms specific issues in practice. Optimize for data integrity. Yep, same rule. When can a table be in third normal form but not voice code normal form? When Raymond F. Boyce and F. decree it so from on high. I wonder if they're still around. It has multiple possible primaries. It has multiple possible primary key combinations, and one of the columns in a possible primary key is dependent on a column outside of that primary key. There's a primary key that depends on another column that is not a primary key. Normalization review. So, in my opinion, the exact definitions of first, second, third, and voice code normal forms simply are not all that important in your work as a backend developer. However, what is important is to understand the basic principles of data integrity and data redundancy that the normal forms teach us. Let's go over some rules of thumb that you should commit to memory. They'll serve you well when you design databases and even just in coding interviews. So, rules of thumb for database design. Every table should always have a unique identifier primary key. 90% of the time, that unique identifier will be a single column named ID. Avoid duplicate data. Avoid storing data that is completely dependent on other data. Instead, compute it on the fly when you need it. Keep your schema as simple as you can. Optimize for a normalized database first. Only denormalize for speed's sake when you start to run into performance problems. We'll talk about speed optimization in the later chapter. Which should you optimize for first, speed or reducing duplicate data? When do you not need a composite key? When you don't need a composite key, what should the name of your primary keys column be? Skeleton key, key, identifier ID. Which is more important than your career in backend development? Memorizing the exact definitions of first, second, third normal form and voice code normal form. Internalizing simple rules of thumb regarding database normalization. We're getting there. Got an hour left and we've got two chapters. I'm sure we'll be able to do it. So, banking relationships. So someone added new columns to CashPal's users table that include information on the user's banking institution. Unfortunately, the developer that made these changes had assumed that a user could only have a single banking institution. We know that a user can be We know that a user can be a member of multiple banks, and banks can service a great deal of CashPal users. You've been tasked with cleaning up users table and creating an additional table and any additional tables to properly support many-to-many relationships between banks and users. So, assignment. Given what you've learned about normalization and many-to-many relationships, do the following. Create a new table called banks. So, create table banks that contains bank-related columns that were incorrectly added to the users table and that were prefixed with bank. Be sure to remove the bank prefix and create the table. We don't need it. Be sure to remove the bank prefix and create a table. We don't need it anymore. Don't worry about altering the users table right now. Oops. No. Create a joining table named users bank. So create a table users banks with user ID and bank ID columns. So user underscore ID integer and then bank underscore ID integer. Add any constraints such that it is never duplicate row with the same user ID and bank combination. And I think it was constraint. Or wasn't there like a unique thing? A unique user underscore ID and bank. Oops, bank underscore ID, is that it? Whoops. Simple as that. Okay. 2 chapters left. Joins. Okay, so joins are one of the most important features that SQL offers. Joins allows us to make use of the relationships that we have set up between our tables. In short, joins allow us to query multiple tables at the same time. So inner join. The simplest and most common type of join in SQL is the inner join. By default, a join command is an inner join. An inner join returns all of the records in table A that have matching records in table B, as demonstrated by the following Venn diagram. Data that matches between 2 tables, so on. To perform a table join, we need to tell the database how to match up the rows from each table. I need to put another thing on. Yep, one more. How to match up the rows from each table. The on clause specifies the columns from each table that should be compared. When the same column name exists in both tables, we have to specify which table each column comes from using the table name or an alias followed by a dot before the column name. So for example, this, so in this query, employees.department ID refers to department ID column in the employees table. Departments.id refers to the ID column in the departments table. The on clause ensures that the rows are matched based on these columns, creating a relationship between the 2 tables. The query above returns all fields from both tables. The inner keyword only affects the number of rows returned, not the number of columns. The inner join filters rows based on matching department ID and ID, while the select star ensures all columns from both tables are included. Why is this important? In many databases, different tables might share the same column names, such as ID. If you don't specify the table name or alias for a column, the database won't know which column to use for the join. For example, writing on ID equals ID won't work because the database can't distinguish between ID columns in each table. Assignment. Our front-end team is working on a profile page and would like to display a user's country name instead of just the country's 2-letter code. Let's start by writing a simple join between users table and countries table. We'll expand on this query more in the next exercise. So write an inner join between users and countries. So users, countries, so country code, country underscore code, users, countries dot country underscore code. Easy. Namespacing on tables. So when working with multiple tables, you can specify which table a field exists on using a dot. For example, table name dot column name. Okay, so select student.name and classes.name from blah blah blah. The above query returns the name field from the students table and the name from the classes table. Assignment. Adjust the query to return name, age fields from users table. So name, users dot name, users dot age. Return the name field from the countries table and rename it to country country name. Countries dot name as country underscore name, like that. Whoops. Sort by the country name in ascending order. Okay, so sort order by country. Just got name. Ascending. Here we go. So left join. A left join will return every record from table A, regardless of whether or not any of those records have a match in table B. A left join will also return any matching records from table B. Here is a Venn diagram helping visualize the effect of left join. So left join, all of table A data matching and matching data from table B. Okay, a small trick you can do to make writing the SQL easier is define an alias for each table. Here's an example. Okay, notice that the simple alias decorations here, E and D for employees and departments respectively. Some developers do this to make their queries less verbose. That said, I personally hate it because single letter variables are harder to grok, so you don't use them in this course. Assignment. The Cash Pal team needs to report on all transactions a user has made. Join the users and transactions tables on the users.id and transactions.userid. Your query should return 3 fields, so select user's name is name, so users.name. The sum of all the transactions amount is sum, so sum transactions dot amount as sum. The count of all the transactions is count transactions as count. Be sure to group the data by user's ID from what is it? Users left join transactions on. Be sure to group the data by the user's ID. Be sure to order the data by a sum field in descending order. So on users dot ID is equal to transactions. Transactions. What was it? User ID. Transactions dot user underscore ID. Order by sum ascending. Do not alias the table names, this will fail the lesson. Try it. No such column transactions. Be sure to return users records of users who have no transactions. Do not alias the tables to fail lesson. So this bit, sum of all the transactions amount is sum. The count of all their transactions is count. Yeah. Be sure to still retain user records for those who have no transactions. Be sure to order the data by some field sending. Be sure to still return user records of user who have no transactions. So yeah. Be sure. User's ID, transaction user's ID. Be sure to still retain users records for users that have no transactions. What am I missing? You're very close. Think about too many aggregations related instructions from the lesson. So be sure to group data by user's ID. Be sure to order the data in some descending order. Okay, so now compare your query. Are you using group by clause yet? Is your order by using ascending or descending? It's using ascending. Try adding appropriate group by and adjusting the order by direction. Oh, descending. Whoops, read that wrong. So I guess it's group by user start ID. There we go, got it. So right join. A right join is you expect the opposite of a left join. It returns all records from table B regardless of matches and all the matching records between the two tables. A right join is just a left join with the with the order of the table switched, so in most cases left join is preferred for readability. We can retrieve the same records from a right join and a left join by grouping the table by a different field, giving up and drawing Venn diagrams, flipping the position of the tables in the join statement, changing the field of the names they are joined on, flipping the position. Full join. A full join combines the result of the left join and right join commands. It returns all records from both table A and B regardless of whether or not they have matches. What's the best scenario to use a full join? You need the matching results from two tables, every single row from two tables, whether they are or not they're related, all results from a single table, all results from one table, matching results from everything basically. Given the tables and query, which join type would produce the result? Left join. No, inner join. Given the tables of query, which join type would produce the result? Left join. And then joins quiz. Yeah, there's full join. Oh, sorry, right join. Join practice. Joins take some time to get used to, but the key to understanding them is using them effectively in practice. So multiple joins. So to incorporate data from more than two tables, you can utilize multiple joins to execute more complex queries. So an assignment. Our front-end team is finalizing the profile page for CashPal. We need to write a query that returns all the user data they need for an individual user's profile. A query needs to return the following fields: the user's ID. So start with select. User's ID, user's name, user's age, user's username, the user's country name, renamed to country name, the sum of the successful transactions from the user, renamed to balance, return only a single user record, specifically the one with ID 6. Okay. Whoops. So it's going to be users.id, users.name, users.age, username, country name, we need country name. So countries dot name as country underscore name. The sum of successful transaction from user name to balance. So sum of transactions. So I guess it's going to be like if statement. As balance. users so left join on countries on, so it's going to be users dot here's the ID, it goes countries dot user underscore ID, inner join transactions on users.id, .id, what's going on with me today, equals transactions dot user underscore ID, where transactions dot was score successful equals true. And users dot ID is equal to 6. Try that off the bat. So user ID, user's name, user's age, whoops, extra comma. I think I've done all this. Countries.user ID, what's it called then? Country code. Country underscore code. Country underscore code. Bingo bash go. User support tickets. So CashPal stores customer support requests in a support tickets table. A recent bug caused a flood of account access tickets hiding other important issues. Now that the bug is fixed, support wants to focus on users with multiple non-account access problems. So assignment, write an SQL statement that includes an inner join and returns the following. Select users dot name, users dot username, the count, and it's going to be a count of tickets attributed to that user labeled as support ticket count. Users, support tickets, user ID. Count of support tickets. Support underscore tickets underscore count from users in a join and what was it, support underscore tickets on users dot ID is equals to support underscore tickets dot user underscore ID. where this whole bit is equal to account access. Only returns records for users who have more than one support ticket of another type. The counter support tickets attributed to that user labeled as support ticket count. Exclude any tickets that have account access as the issue type. Oh. Exclude any tickets that have account access as the issue type on return records for users who have more than one support ticket. Who have more. So all the records by using the most important ticket at the top. So okay, so order by support underscore ticket underscore count descending. Or returns records for so exclude any tickets that have account access. Only return records for users who have more than one support ticket of another type. What? The count of support tickets attributed to that user labeled as support ticket count. Oh, I need to group by. Oh, no, not quite. Uh, just gonna, I want to speed this up. So, how close am I? Come on, Boots. Okay, you're on a good track. Go coder bear, but a few details are off. The assignment says only return records for users that have more than one support ticket of another type. Right now you're grouped by blah blah blah. Are you grouping by user or by issue type? Well, you should group by if you want. All right, okay. Okay. You should go if you want to per user counts. You're counting. That's fine, but look at the group by again. If you group by user, what will count represent? The assignment wants you to exclude users with only one such ticket. Where could you add a condition like count is greater than one? Hint, it should go in where or having when you're. Should it go in where or having when you're using count? It's going to be, I guess, in having when using counts. Is greater than one. Finally, we want users with the most support tickets at the top. We'll group by to be per user. Add a condition to only keep users with more than one ticket. Then keep the order by using that count. How about now? Much closer, why is one? Just a tiny mix up with where to filter out the account access. Having is for conditions and aggregates. Where having. Boom, got it. Okay. Right, so we're on to the last bit. Let's get this done before 10 o'clock, so half an hour. An index is an in-memory structure that ensures that queries we run on a database are performant. That is to say, they run quickly. If you can remember back to the data structures course, most database indexes are just binary trees or B trees. The binary tree can be stored in RAM as well as on disk, and it makes it easy to look at the location of an entire row. So primary key columns are indexed by default. Ensure you can look up a row by its ID very quickly. However, if you have other columns that you want to be able to do quick lookups on, you'll need to index them. So create an index. So create index name on table, blah, blah, blah. It's fairly common to name an index after the column it's created on with a suffix of IDX. Assignment. As it turns out, the front end frequently finds itself in a state where it knows a user's email but not their ID. Let's add an index to the email, call it email IDX. So create index email and it's got IDX on what's the table? Users email. Index review. As we discussed, an index is a data structure that can perform quick lookups. By indexing a column, we create a new a new in-memory structure, usually a B tree, where the values of the index column are sorted into the tree to keep lookups fast. In terms of big O complexity, a B tree index ensures the lookups are O log n. Shouldn't we index everything? We can make the database ultra fast. While indexes make specific kinds of lookups much faster, they also add performance overhead. They can slow down a database in other ways. Think about it, if you index every column, you could have hundreds of B trees in memory. That needlessly bloats the memory usage of the database. It also means that each time you insert a record, that record needs to be added to many trees, slowing down your insert speed. The rule of thumb is simple. Add an index to columns you know you'll be doing frequent lookups on. Leave everything else unindexed. You can always add indexes later. A B tree index makes lookups O to N exponential, O n log n, O n, or O log n, he said. Add indexes to only primary keys, only foreign keys, columns that you frequently perform lookups on, all columns. Indexes slow down write speed, because inserts. Multi-column indexes. So multi-column indexes are useful for the exact reason you might think. They speed up lookups that depend on multiple columns. So create an index. A multi-column index is sorted by the first column first, the second column next, and so forth. A lookup on only the first column in a multi-column index gets almost all the performance improvements that it would get from its own single column index. However, lookups on only the second or third column will have very degraded performance. Rule of thumb. Unless you have specific reasons to do something special, only add multi-column indexes if you're doing frequent lookups on a specific combination of columns. Assignment. We frequently need to look up all transactions between two specific users. There's a page on the website that allows a user to look up all the payments they've made to a friend by that friend's name. Add an index on the user ID and recipient ID columns called user ID recipient ID IDX. Make sure user ID in the first column is the index, so we can also use this index to speed up our queries that only care about user ID. So it's going to be user underscore ID recipient underscore ID. I spelled it wrong. I think I did. Oh, transactions. Whoops. Transactions. There we go. Denormalizing for speed. So we left you with a cliffhanger in the normalization chapter. As it turns out, data integrity and duplication come at a cost, and that cost is usually speed. Joining tables together, using subqueries, performing aggregations, or running post-hoc calculations take time. At very large scales, these advanced techniques can actually become a huge performance toll on an application, sometimes grinding the database server to a halt. Storing duplicate information can drastically speed up an application and needs to look it up in different ways. For example, if you store a user's country information right on their user record, no expensive join is required to load their profile page. That said, denormalize at your own risk. Denormalizing a database incurs a large risk of inaccurate and buggy data. In my opinion, it should be used as a kind of last resort in the name of speed. So denormalizing database can be used to speed up queries, slow down queries, speed up. It's smart to start with a blank database and a blank it as needed for speed, a normalized database and denormalize for speed. A blank database is easy to keep bug free, a normalized. So last two chapters or lessons. SQL injection. SQL is a very common way hackers attempt to cause damage or breach a database. One of my favorite XKCD comics of all time demonstrates the problem. Hi, this is your son's school. We're having some computer trouble. Oh dear, did he break something? In a way. Did you really name your son Robert Winky Face Drop Table Students? Oh yes, little Bobby Tables we call him. Well, we've lost his year's students records. I hope you're happy, and I hope you've learned to sanitize your database inputs. The joke here is that if someone was using this query, insert into student's name values blank, and the name of student was Robert drop table students, then the resulting SQL query would look like this. As you can see, this is actually two queries. The first one inserts Robert into the database, and the second one deletes the students table. How do we protect against SQL injection? You need to be aware of SQL injection attacks, but to be honest, the solution these days is to simply use a modern SQL library that sanitizes SQL inputs. We don't often need to sanitize inputs by hand at the application level anymore. For example, the Go Standard Library's SQL packages automatically protect your inputs against SQL attacks if you use it properly. In short, don't interpolate user input into raw strings yourself. Make sure your database library has a way to sanitize inputs and pass it those raw values. So SQL injection is avoided by using a modern SQL package that handles the sanitization of user provided values. True. What happened in the comic? Robert's grades were changed all to be A's. Robert's data was deleted. Every teacher's data in the school's database was deleted. Every student's data in the school's database was deleted. All the students were gone. Hey, and we're done. I'm going to claim all that. Boom. Great course once again. I never felt overwhelmed. Learning the normalized forms was interesting from a specific definition perspective. There should the examples were good and overall a great refresher for me. Can't fault it. I'll skip it for now. And then now it's going to be all the fun stuff. Just open all the chests I got. Hey, sharpshooter, 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 sharpshooter. I'm locked at Sage. I'm the top 1%. Whoops, hold on, I just realised. Here we go. I already claimed my reward. All the vibe. We all know it. We all love it. We all use it. it's fun to it's always good to run through the basics every once in a while. I don't regularly need regularly deal with SQL anymore, and it's easy to forget how powerful it is. We forget it's a full language in its own right, not just a database, not just a data lookup tool. Awesome course by Boot and Boot. Once again. Let me know what's your favorite SQL databases. SQL types. Well, SQL Lite, relational databases. key. Okay, that's posted. I guess we're done. So we'll be coming back next week at some point, I'm not exactly sure when, to build the blog aggregator in Go. We're getting closer. I don't know if it's going to be possible to hit the milestone we wanted before the end of the year that I gave myself. It's like somewhere in January. In fact, I'll be able to see my profile thing. Let me have a look at it. Joined 9th of January, so it's like I'm not sure if I can get there in the end. We're early in December, so I guess if I did like 1 2 3 4 5 6 7 yeah, I mean capstone projects and learn how to find a programming job, like capstone projects I'm definitely not going to get done. Like I have to come back to that, but the other ones I could possibly get done. But the capstone project I want to build, like, something worth shouting about, so I might even just skip that one. So 1 2 3 4 5 6. It's doable with some with some push, but that's going to be it for tonight. So that's going to be it for tonight. Yeah, we'll come back next week and we'll try and tackle another course and kind of keep going from there. But as always, thanks for watching. Thanks for coming down. If you come from the future, let us know where you got that time machine from, and I'll see you next time.